matching, we also need to extend our algorithm to handle recursion. Recall from our last lesson that recursion in Haskell can be implemented using the fix function that recorded in the meta environment. So it was defined as a fix applied to f and is reduced to f applied to fix of f. So assuming that fix is given in prelude, which is type is already have been recorded in the gamma init, which is say for all alpha, and alpha goes to alpha and return alpha. And we can use this information and apply what we learned early on to infer the type of the following programs. Derivation of the example of the sum2 that we had seen in the last slide. We started off at the bottom of this slide. So we were trying to infer the type of the program that fix apply to this lambda, with lambda g goes to lambda n, case n of, in case it's 0, we return 0, in case it's x, we return n plus g applied to n minus 1. So as a notation, I will use the red as for some temporary variable assignment or symbol assignment. For the blue, often I use it to denote the output. Hope that I remain the consistency throughout the explanation. So first of all, over here we look at the shape of the program is a function application, and then we first, since the application, we apply the app rule. We look at this symbol fix. So we look at these subdeclarations. So since fix is actually a variable and is recorded in the init environment, we then look it up in the init environment, apply the ins rule to monomorphize the type scheme into alpha 1 to alpha 1 to alpha 1. Okay, so this is the type of fix. Okay, then we look at the right hand side, the actual argument, okay, which is the lambda and g right hand side. Okay, right arrow lambda n case of this, which is given here. Okay, so we look at the program, a subprogram in this case, which is a lambda abstraction, and so we apply the abs rule. For now, we pretend we don't know what's the output first. Okay, so we apply the abs rule here, and which says that we first need to create a new variable. Let's call it alpha 3. Okay, iteration of the sum2 example. We are trying to infer a type of the definition of sum2, which is fix applied to this lambda term that involve lambda g, right arrow lambda n, and right arrow case n of pattern matching. In case is 0, then return 0. In case it's x, we return n applied to g applied to n minus 1. So for given this expression is actually a application, so we're going to apply the app rule. For some color so-called terminology, sometimes I'll use the blue to denote the output, but not always, but I try to maintain this consistency. For the red is always used for some temporary variable or symbol alias. Okay, let's look at the app rule here. Because it's application, so we need to first find out the type of fix. So we then look up fix from the gamma init, which give us is a for all alpha, alpha goes to alpha and return alpha, and we immediately apply the inst function to it, and will give us a simple type that is from alpha 1 to alpha 1, and this is an input parameter and return alpha 1. Okay, to unify it with the actual argument, and we first need to create a temporary variable or new unification type variable called alpha 2. So we're going to use that later on for the MGU here. But before we look at that, we first consider the actual argument type. So to infer the actual argument, we have to look into this sub-expression, which is lambda g, right arrow lambda n, and case, so on and so forth. And again, for now, we ignore the blue part, which is output. And by looking at this expression itself is a lambda abstractions. So we apply the abs rule here. First, we're going to create another new unification type variable called alpha 3, and we're going to give g, which is the formal argument, the type alpha 3, and we're going to extend the type environment with this g alpha 3, and let's call this gamma 1, under which we're going to infer the type of the body of these lambda abstractions, which is itself is another lambda abstraction that is lambda n case expressions, and hopefully will give us some result, and then we can use it for unifying alpha 3 with that result, okay, to create a function type. For now, let's ignore the output. We come back to that later on when we finish looking at the subdeclaration on top. Okay, again, this is the abs rule. We're going to apply the abs rules here. Then we have to create one more unification variable, type variable called alpha4, and we're going to record in a type environment that the formal argument n would have the type alpha4, and let's call the extended type environment gamma2. And under this new type environment, we want to infer the type of the case expression, which is a body. They have some type, okay? And then we look at this one, and because this is a case expression, so we're going to apply the case rule. For the case rule, we have to first create another unification variable called alpha phi, which is serve as the output type of the entire case expression. Hopefully some NGU would unify to some ground type. Let's look at the inference of the expression, conditional expression variable, which is n. So under gamma2, we would like to infer the type of n, so which is obviously is alpha4 because we have extended it here in the type environment gamma2. So under gamma2, we know that n has a type alpha4, so we insert alpha4, we get back alpha4. So now we know that the input or the conditional expression has type alpha4, and we're going to use that information to infer each individual pattern. So this rectangle denotes the inference for the first pattern cross. The bigger box up there denote the inference of the second pattern cross. Okay, let's consider the first pattern cross. So we applied the const pat because this is a constant pattern. Given the input type is alpha4 and 0 as a pattern, so we construct the unification that try to unify the int, which is the type of the pattern, with the input type alpha4. That will give us replacing alpha4 by int. So this is the output substitutions and output type environment, which is empty type environment. And then we're going to use this, okay, to improve our type environment, because this doesn't give us extra information about type environment, only the substitution. So we're going to apply this type substitution to our gamma2 and try to infer a type from 0. It turns out that we don't need to use anything from here because the right hand side, which is a 0, is obviously a constant expression, and they have type int, which returns empty substitutions or identity. Okay. So that is for the first subpattern. The second pattern clause. So given that alpha4 is the input, so over here we do not have the information that alpha4 is int. Okay, assume that we don't have, because the information was from the previous subpattern. So at this stage we don't have the information about alpha4 could be int. So we're going to infer that the patterns x, okay, would create the type environment that x has a type alpha4, because this is the var pat rule that will create a empty type substitutions, and we're going to use this information to apply to our gamma2. But since this is empty, it doesn't improve gamma2 at all, and we're going to infer the right hand side of this pattern clause, which is n plus g applied to n minus 1. Okay, and by looking at this one, we use the app rule, because now this is function application. So we first need to create a result type variable alpha6. Okay, is a new unification type variable, will serve as the return type of this function application, entire function application, and hopefully some inference will ground it. And we look at the inferring the type of the function expression, which is plus n, which is treating the plus sign as a prefix functions. So we try to infer this one, and this expression itself is a application again. So we apply the app rule here, and which requires us to create another alpha7, which is the result type of these applications. We're going to ground it later on, and then we going to first check what is the type of the plus symbol. So in this case, we figure out that while plus is actually a predefined function in our gamma init and as well as in our gamma2. and applying inst function to this will give us int to int to int, and this is the type for the plus. Okay, it return an empty substitutions. Next, we look at the actual argument, which is n. So under the gamma 2, n has a type alpha 1, obviously, because that's how we recorded gamma 2 here. In gamma 2 here. So n has a type alpha 4, and we try to instantiate it, and we still give us alpha 4, and then this would give us empty substitutions. Next, we're going to perform a unification on the this type, okay, which is the plus type, and the alpha 4, which is the actual arguments type, and alpha 7, which is the return type of the function application. So if we apply MGU of this, we'll get back the substitution, like we replace alpha 4 with int and alpha 7 with int to int. So therefore, the result, the type of this one will be applying this substitution to alpha 7, but for simplicity, since alpha 4 is not mentioned here, I just show you it's int to int replace alpha 7. So this obviously will give us int to int, because alpha 7 is int to int, and we will keep this substitution as the output substitutions. So that would be the derivation for inferring this sub-expression. Next, we have to look at the other actual argument, which is the g applied to n minus 1. So because we completed this part, we have to look at the type of this. What is the type of this? So the derivation is over here. So we're going to make use of this side 1, which is the output type substitution of these expressions. We're going to apply psi 1 to gamma 2. Hopefully you can improve it first. And under this new environment, we're going to infer the actual argument, which is g applied to n minus 1. We'll have some type alpha 8, and then these are the output substitutions. We're going to see that in the next slide. Psi 1 to gamma 2 and try to infer the type of g applied to n minus 1. And over here, we first need to create a new unification type variable, which is alpha 8. Okay, and then we're going to infer, we're going to look up the type of the function expression, which is g, and notice that g already given a type alpha 3 in our gamma 2 environment. Okay, so we try to instantiate alpha 3, that will give us alpha 3. So therefore g has a type alpha 3. Then we're going to look at the actual argument, which is n minus 1. So under the psi 1 applied to gamma 2, we would like to infer the type of n minus 1. So again, this is an application. So we need to first create another unification variable called alpha 9. And then we would like to infer the function expression. So again, I rewrite this in the prefix style, where the minus appear in the front. So we first need to infer minus n. And for this sub-expression itself is again another applications. So we apply the app rule here. And first, we would need to create a new result type variable, alpha 10. And then we infer the type of minus, which is obviously is from int to int and to int. That will give us the empty type substitutions. And then we look at the actual argument, which is n. So under the psi 1 applied to gamma 2, we would already find that n actually has a type integer. Initially it was some other alpha 4, but because of presence of psi 1 that has a substitution for that alpha 4 to int, so this will give us int. So n will have type int with the empty type substitutions. So given this information, now I can construct a MGU between the type of int to int to int, which is here, and also the int, which is coming from n, and also alpha 10, which is the result type. That will give us alpha 10 has a substitution int to int. And with this information, we propagate down here, and we're going to apply this int to int with alpha 10 to alpha 10 is that because it's the result type of this, and this will obviously give us int to int. Okay, and so since this is from int to int, and I need to look at the actual argument of this one, which is 1. Okay, 1 obviously we can infer that it has a type int. So we need to construct the MGU between alpha 9 int and as well as this alpha 10 is actually int to int. So this is my alpha 10, this is my alpha this is my alpha this is actually the type coming from the 1, and this is alpha 9, and applying the MGU over this will give us we can replace alpha 9 with int. So again we combine these two substitutions, we form a bigger one, which is this one. Then we're going to apply it to alpha 9, which is because alpha 9 is the output type of this applications, so that will give us actually int. So this will give me int, and we compose the two substitutions together, we get back int to int that replace alpha 10, and int we replace alpha 9, and we again create one more MGU to unify the alpha 3 here, that is our function type, and int right arrow alpha 8. Alpha 8 was created temporarily as the return result type of this application, where int was coming out from here because we apply the substitution to this one, alpha 9, that will give us int. So this is the actual argument type with respect to this expression. And if you unify these two, you give us the information about you can replace alpha 3 by int right arrow alpha 8. But we don't know what's alpha 8 yet. So it's fine. We're going to apply this substitution to alpha 8, and then we keep the entire substitution is like int to alpha 8 that we would replace alpha 3, int to int replace alpha 10, int replace alpha 9. We have propagated from the subderivation of this inference. We have alpha 8 here, which is not yet grounded. We have the substitution that output from there. So now let's say we have to look at this application. Okay, so we have the information of this sub-expression and n plus. So n plus recall has a type alpha 7. If you apply the substitution, we get actually int to int. So we're going to unify int to int with this is alpha 8. Okay, the alpha 8 is the actual arguments type, and the alpha 6 was created as the return type of this application. So we're going to unify this two type. That will give us like int replace alpha 8 and int replace alpha 6. Okay, and let's say we combine this one with psi 1 and psi 2, which come from here, psi 1 come from here, and this will be called psi 2. Okay, so psi 2 apply to alpha 6 because alpha 6 is the return type here. So that will give us int. So the entire type for these expressions will be int, and psi 2 will be the return substitutions. So now we have completed inferring the type for each of the pattern clauses. So it's time for us to unify and consolidate all the type substitutions. So first of all, we would like to perform the unification on among the alpha 5, which is the output type of the case expression, with all the return type of this pattern clause and that sub pattern clause, so which is int and int. And we will perform MGU on this. That will give us the information that we're going to replace alpha 5 by int. So let's call this psi 4. Okay, so and at the same time we also collected the substitution with all the individual pattern inference. Let's say this empty substitution, and as well as this, okay, that replace alpha 4 with int. Let's call this psi 3, and we compose psi 4, which is this one, and with psi 3 and psi 2. Psi 2 is coming from here, and we're going to apply this substitution into alpha 5, which is the output type of this case expression. That will give us the information that replace alpha 5 with int. Okay, so this will become int, so which means that the case expression has type int, and the return type substitution is psi 5. Okay, and we propagate down further. So since we know that the alpha 4 was actually created here for the lambda, so we're going to ground it here. So we know that this is a lambda abstractions. It must have a type from alpha 4 to the result type. The result type of the case is actually int. We already know that. Okay, so it's alpha 4 to int. If we apply psi 5 to this alpha 4 to int, we'll get int to int because alpha 4 was grounded with int. somewhere on top, which is here. Okay, in side 1 they propagate to side 2, and then because side 2 was part of side 5, so we are able to ground alpha 4 with int. So this will give us the output type int to int, and the output substitution is side 5. Then we have looked at back this abstraction rule. Again, we have to ground this type, which is, we know that G has a type alpha 3, and the result type is int to int, so it's alpha 3, right arrow int to int. And we already know that alpha 3 is being grounded as int to alpha 8, and then we know that alpha 8 is actually itself is also int. So the alpha 3 will become int to int, and this remains the same, int to int, and we return alpha 5 side 5 as the output substitution. So far so good, and we are coming back to the main step. That is, we need to perform a unification between the function type, which is alpha 1 to alpha 1 to alpha 1, with the actual argument type, which is the type of this one, which is int to int to int to int, which is here. And then alpha 2 was created as the output type of this entire application. So we're going to perform the MG of these two. That will give us something like replacing alpha 1 with int to int, replacing alpha 2 with int to int. So that would give us the answer by replacing alpha 2 with int to int here. So the whole expression will give us int to int, and the output type substitution will be this substitution composed with our psi 5. So in a way that this expression will have type int to int.